Welcome to this presentation. The title is High Temperature Erosion of Oxide Coatings Deposited by Atmospheric Plasma Spraying and a Hard Facing Coating by Shielded Metal Arc Welding. My name is Eduardo Rodriguez, and let us read the background. Erosion by solid particles at high temperatures occurs in industries such as petrochemical, metallurgical, cement, coal-fired, thermal power station, garbage incineration, and fluid acid-based combustion systems. To improve this wear resistance, coatings such as ceramics and metal ceramic composites are used, which can be applied by techniques such as thermal spray and hard facing. There is a clear shortage of studies on high-temperature erosion of alumina, the combination of alumina plus chromium oxide ceramic deposited by thermal spray, and high-temperature hard-facing materials, and no comparative study between these materials has been found. Therefore, in the present work, we propose to perform room temperature and high-temperature erosive wear resistance tests on alumina plus chromium oxide ceramics materials deposited by atmospheric plasma spray and in high-temperature hard-facing coatings, and thus perform a comparative analysis of the erosion behavior of these coatings. On the lower image, we can see real problems of materials under high-temperature erosion. For the experimental part, we have both raw materials shown in the pictures, alumina alpha powder and alumina plus chromium oxide powders. The X-ray diffraction patterns are shown in the lower part. We have the orange colored for the alumina and the red pattern for the chromium oxide plus alumina. Both of these powders were projected by plasma spraying as is shown in the picture. In the table is shown the projection parameters by the Suresa factory for both materials, alumina and the combination of 25% alumina plus 75% chromium oxide. For the erosive system, a sandblast type rig was used. In the upper part, the sand is poured. In the middle part, occurs the combination of the air and the erosive silica sand. And finally, at the lower part is the furnace chamber, where the sample is eroded at a high temperature. In the lower picture, the inner part of the furnace is shown. It can be seen the exit nozzle and the specimen holder in a high temperature atmosphere. The erosive particles were silica sand with a size distribution shown in the pictures and in the bars graph, with the average size particle of 150 microns. In the table is shown the erosion parameters used for the erosion testing: two temperatures, room temperature and 600 Celsius degrees, semi-angular silica sand, 5 pounds of air pressure, and 3 impact angles were tested: 30, 60, and 90 degrees. Impact particle speed was of 58 meters per second, measured by the double disc method. Results. In the first picture, it can be seen the cross-sections of the coating of 500 to 600 microns, and the second image is a high magnification of the first one, showing the combination of chromium oxide splats and the alumina splats. The white phase corresponds to the chromium oxide. The X-ray diffraction shows the presence of both phases. The lower picture shows the microstructure of the hard-facing coating deposited by welding. It can be seen the dendritic growth, and in the scanning electron image, a mixture of several phases. The microanalysis EDS shows the presence of iron, carbon, and carbide formers as chromium, niobium, molybdenum, and so on. This is the typical microstructure of the hard-facing coating. The microhardness for the three coatings were 800 for alumina, 870 for the mixed ceramics, and around 700 for the hard-facing deposition. The central graph is for the room temperature condition, black bars for the alumina and red bars for the mixed ceramics. For both ceramics coatings, the increase of the erosion values is evident as the impact angle increases. This is known as brittle behavior of the material in erosion testing, but the mixed ceramics composition was a little bit stronger than the alumina alone. As can be seen on the same graph, the blue bars correspond to the hard-facing coating, and it is the strongest for all impact angles. For the high-temperature erosion values, 600 Celsius degrees, there was a brittle behavior for the ceramics, as in the previous case, but for the alumina coatings, there was an apparent decrease on the mass lost. It was explained due to the adhesion of silica from the erodent particles, and this happened only at high temperatures, as can be seen on the image below the graphs. Again, the hard-facing materials, the blue bars, showed the best results. On the first three images, the erosive mechanisms are presented for the alumina coating, and they explained the big amount of the erosion of the ceramic samples when the impact angle is increased. It can be seen that the scars marks increase as the impact angle increases. In the lower left image is evident the brittleness of the ceramic, showing no plastic deformation and an easy crack formation and propagation. In the last two figures, it's easy to see the plastic deformation for the hard-facing coating, on which the hard carbides and the iron faces makes a cermet materials with the best results. Conclusions. 1. At room temperature, the mixture of alumina 25% and chromium oxide 75% mixture showed highest hardness and better erosion resistance when compared to the alumina alone. 2. At 600 Celsius degrees, the silica sands adheres to the alumina coating, causing a lower mass loss measurement. Of the three coatings, hard-facing welding showed the best resistance for both room temperature and high-temperature erosions, which is attributed to its structure being similar to that of cermets, having ductile wear mechanism due to the large amount of high-temperature resistance metallic phase. The behavior under the erosion of ceramic coatings, both alumina alone and the mixture of the alumina plus chromium oxide, was always brittle. That means maximum wear at high impact angles for both temperature conditions, with erosion mechanisms due to the brittle fracture. Thank you for your attention.